Bismillahirrahmanirrahim. Greetings. Euclidean algorithm is a repeated division starting with two given natural numbers and ending up with their greatest common divisor. Now, in the previous lecture, I have demonstrated the concept pictorially. Now, in this lecture, we are going to see the mathematical proof of that. So what really is going, in order to make the proof kind of more comprehensible for the beginner students, I am going to set up the algebraic equation correspondence with respect to an example of my own. And then I go through the entire algebraic steps, and then and the mathematical proof of that. And what really is going to happen before I zoom it and stay out of where I'm going on the board is that we have division, which means we have numerator, denominator. The numerator is called dividend, denominator is called divisor. Then we have quotient and remainder. Is that right? Now the next step is that the divisor, the previous divisor, become dividend. And the remainder, previous remainder, become divisor. And that gives us a new quotient, a new remainder. And these steps will follow until the end, and the greatest common divisor will be achieved. So let me zoom this one and go and stay out of way and do it on the board. Shall I? May I? Okay. Here is the number, the example that I did mention. This is an example of my own. This is called dividend, this is divisor, this is quotient, and this is what remainder. And the corresponding algebra of the corresponding algebraic form of that will be A over B equals to where A is A is what? Dividend, B is divisor, Q is quotient, and R is what? Is the remainder. This is algebraic correspondent to this example. Where A and B are natural numbers, and of course in this proof we assume that A is greater than B, and that is without loss of generality. A is bigger than B. If A equals to B, is a trivial case. So now, look what happened for the next step. For the next step, I'm going to, in this example, if I multiply both sides by 1701, I get this one. Is that right? And same is true here. If I multiply both sides by B, I get this one. So this is the algebra equation corresponding to this numerical example. Now, here, these two are equivalent, these two forms. They look different, that's what the meaning of equivalent means. They look different, but they are same. They have same meaning. So instead of following this form, I'm going to follow in this kind of linear form, which is a bit easier to work with. I could go through this one, but as I said, this is a bit easier, and this is same as this one. So what happens here, this is my dividend, this is my divisor, and multiplier, and the remainder in this case will be 366. When I divide 1701 into 3768. And the corresponding algebra of that I already mentioned is this, and I'm working with subscript. So this is Q1 and R1. I hope it's clear as a subscript to distinguish them. So the next one will be this one, and look what happens in this one. The divisor, the previous divisor, become dividend, and the remainder become divisor. You see that? And then we have a new quotient, and we have a new what? Remainder. And that's exactly the corresponding algebra part of that is, which is what the divisor become dividend. You see that? The remainder become what? Divisor. So we have a new quotient, which I put it Q subscript 2 plus remainder. Again, I put it with the subscript to distinguish them from the previous one. So this will be subscript 2 or subscript 2. And this algorithm will follow all the way to the end. I read that, and I don't have to really go further and explain. You can see it in the that's primitive primitive equipment I have. Now, as you notice here from this example, let me put this one here if I may. Now, as example, as you can see, the example end up to 0. You see that? And then the number before that, which in this case is 3, will be the greatest common divisor of 3768 divided by 1701. So this is the greatest common divisor of these two numbers. So numerically we can see, you can test it and find for yourself, definitely. And this looks like end up, when we reach 0, then the one before 0 will be the greatest common divisor. But this is numerical. In algebra, we have to prove this one. We have to provide justification for that. So I guess you are clear with that. So with your permission now, I'm going to put the algebra part of it. I keep saying that because of the primitive equipment I have. I have to walk 1 mile round trip to zoom in and out because أنا مسكين ما في زوجة. Okay, now let me go for this one. Let me see if I'm setting it up correctly. Right place. Hopefully I do. I can go and check. Let me go and check to see if it is correct setup. One looks good. Let me a little bit zoom it further. I think it's better now. Am I? Okay. Now we are in algebra. So again, this is dividend, this is divisor, this is quotient, this is remainder, and you can see the divisor become dividend, the remainder become divisor. We have a new quotient, and we have a new remainder. These steps are going to follow. You see that? Now I went up to R, the subscript, I put n minus 5, and then look at this one to set up my subscript in terms of n. Now look at this one. This one, the subscript is 3, then the next one, this one is 1 more, which is 4, you can see that? And this is 2 more than that, which is 1 more than that, which is 5, and this has the same subscript as the quotient has, which is 5 also. That's exactly what I'm going to follow. So if this is n minus 5, the next one will be 1 more, the subscript. So negative 5 plus 1 is negative 4. So the R subscript of that will be n minus 4. Then the quotient will be n, the subscript will be n minus 3. And then the remainder will be n minus 3 also. Follows this one. And this follow up to Rn minus 3. You follow me? And then again, you can see that how this, if this is Rn minus 3, this will be the subscript of this one will be n minus 2, the subscript of this one will be n minus 1, and the subscript of this one also will be n minus 1. And then we find out at the end here, we end up with Rn as a subscript to be n. Now the question that you may ask, why did I selected the subscript n minus 3 for my last one, so that this one to be n, subscript of that to be n? The answer is that there is no standard, there is no mathematical standard. You could select this one to be n minus, let's say 2, or n minus 1, or even n. You could say that. I think I have one that I'm going to go over that. Now the reason I selected n minus 3 is because I worked in my scratch paper, and I end up, if it is n minus 3, then this will be the subscript of that will be n. So it kind of follows 1, 2, 3, and so on, goes to the n. It was kind of more appealing in my eyes, and it's also, I thought, is easier to kind of explain it. But there is no standard. You could say it n minus, instead of n minus 3, you could say n minus 2. As a matter of fact, it's good to you do it as a practice for yourself. So let me see, I think I have one that I have made it to be, yes I do, fortunately, that I have made it to be Rn. Let me go and explain that one, because you know I'm doing that for the beginner student. For a bit more advanced or mature student, there is no need to explain this one. They have enough good background to comprehend it. So let me now explain this one, if I may. Then I go to the example of that one. Let me see if I'm putting in right place. Okay, now here I go this step by step, then I started with subscript to be n, before I selected n minus 3. So if it is n, then next one will be one more than that, which is n plus 1, according to this example I made. And the next one will be the subscript of q, the quotient, will be n plus 2, and the subscript of remainder will be n plus 1. Do you follow me? And then the next one will be Rn plus 1, because you see, if this is 2, this is 3. So if this is n, this will be n plus 1. And then this will be n plus 2, the subscript. This will be n plus 3, the subscript. And this will be n plus 3, the subscript. Then the last one will be n plus 2 as a subscript. Do you follow me? That I'm going to see that if this is 0, if this ends up to be 0, then this will be the greatest common divisor. Now let me go back to that and try to explain it analytically, in a sense. Okay, let's go back to this one again. Now, here, question that comes is that Rn, the last one, end up to be 0. Let's see why. Now, this raises a question that we have to answer, because we are proving is a mathematical proof, and mathematics is a very kind of meticulous subject that demands justification. So one question it asks us is that how do you know that these remainders will not continue forever? Like continued fractions, some continued fractions, they go forever. So how do you know that goes forever? And how do you know this ends up to 0? And how do you know when it ends up to 0, the number before that will be the greatest common divisor? They are the questions that we have to ask before we go through the proving that this is indeed the case, and this will be the greatest common divisor. Now, to answer this question before we go through the proof for the greatest common divisor, is that these are reducing integers. These are actually positive integers. These are natural numbers. So these R1, R2, R3, and so on and so forth, are up to Rn minus 1, they give us a sequence, a sequence in decreasing order. Now, there is difference between sequence and set. But in this case, our sequence also is a set. A set of what? A subset of the natural number. You follow me? Because all the numbers we are dealing with, they are all natural numbers. We started with A and B to be natural numbers. So each of them are natural numbers, so we are dealing with natural number, and according to the well-ordering principle, every subset of natural number contains the smallest element, contains the smallest natural number in that set. You follow me? Now, well-ordering principle also has its own proof, that is proved by mathematical induction, but we are not going through that. We take that one for granted, and we say according to the well-ordering principle, this set, it is a sequence, as I say, in this case we can call it set, because that satisfies the definition of the set. So this set will have least element. So then after that, this one will be 0. Then you say, hey, not so fast. How do you know this is 0? How do you know that there is no another one smaller than that? So if this one is not 0, then according to this decreasing sequence, there is another integer, positive integer or rational number, which is larger than 0, but smaller than Rn minus 1. In that case, that integer, that natural number will be the least common multiple. In other words, eventually we must end up to 0, and since 0 is not a natural number, but we are dealing with integers, and so the smallest integer in that sequence or in that set, after that cannot be a non-integer rational number, like 1/2 or 1/3. So the only one that he can jump to will be 0. So when we reach 0, then the previous one will be what? Will be the greatest common divisor. Now, let me see if I have another one. I do not. Now, let's see now to prove that Rn minus 1 indeed is the greatest common divisor of A and B. Now, in order, first we show that, this sequence, we show that there is an end, so we have proved and we are convinced with that mathematically. Now, in order to show that is greatest common divisor, first we have to show that it is a common divisor of A and B to begin with. And then after we prove that one, then we have to go next one and prove that this is going to be the greatest common divisor. So let's show first that this is the common divisor of A and B before we justify that it is also the greatest common divisor. Now, how do we prove that this is the greatest common divisor? Now look at what happened. This is 0. Rn is equal to 0. So we show why. So if this is 0, then what happens? Then Rn minus 1, this is subscript, Rn minus 1 divides Rn minus 2, the subscript n minus 2. You see that this is 0, so these two are factors, and like 6 equal 2 times 3, 2 and 3, both of them divide 6. So this divides that one. Now look what happened. When this divides that one, look at this one now. We are going up. Before we were going steps down, now we are going steps up, exactly. So here, Rn minus 1 divides every number, because there is no zero we be afraid of, because we are dealing with natural number. Rn minus 1 is not 0. So this divides itself. Every number besides 0 divides itself. So we have no problem with that. Now Rn minus 1 also divides R subscript n minus 2, because we have shown it in the previous step, that Rn minus 1, the subscript n minus 1 divides that one. So divides itself, divides that one, therefore divides R subscript n minus 3. You follow me? Now, again we are going upward. Now look what happens. We have already shown that Rn minus 1 divides Rn subscript n minus 2 from here. And here, you can see that. Now, here in the second steps going upward, we have also shown that Rn minus 1 divides Rn minus 3. So Rn minus 1 divides this one, Rn minus 1 divides this one, therefore Rn minus 1, the subscript n minus 1, divides Rn subscript n minus 4, R subscript n minus 4. So you know that Rn minus 1 now divides that one. So we can use the same argument and go up and up and up until we reach here. You follow me? It's very, very indeed elementary. Just contemplate, think, reflect, pause, and see what I'm talking about. It's very easy once you get it. Now, when we reach that one, we see that Rn minus 1 indeed divides A and B. Alright? Now, after we show that divides, now we have to show that is the greatest common divisor. We have already shown it is a common divisor. Now we have to show it is the greatest common divisor. Now, in order to show that it's greatest common divisor, because A and B can have, let's say, hundreds of divisors. So this one we want to prove that is the greatest. So suppose that D divides also both of them, is another divisor. Alright? If D divides both of them, A and B, then D divides R1. Do you see that? If D divides A, D divides B, D is better also divide R1. Make an example for yourself. Let's just make a numerical example. Let's say 18 equals to 15 plus 3. Alright? 2 divides 18, the left hand side. But 2 does not divide 15. Therefore, 2 cannot divide 3. You see that? Now, the very same example. 18 equals to 12 plus 6. 2 divides 18. Is that right? 2 divides 12. Therefore, 2 must divide 6. Or another way to look at it, just solve it for R1. R1 equals to A minus B Q 1, in this case the subscript. Then since D divides A and B, left hand side, therefore D must divide R1. So this, again, this procedure continues, come down, come down, come down, come down, and finally ends up to Rn minus 1. That means D divides R subscript n minus 1. The D that we selected, that divides A and B, also divides the Rn sub n minus 1 that we selected to be the common divisor of A and B. So that means any other divisors of A and B will divide this one, R subscript n minus 1. That means R subscript n minus 1 is the greatest divisors of A and B. So we have proved we have done a mathematical proof. This is a analytical proof of that, and we have found out that indeed the one that is the number that is above one step before 0 will be my greatest common divisor of A and B. Okay, let me now zoom and say a few more words, and then we conclude. Okay, then I would like to thank you for watching. If you have any suggestions or comment, please feel free to indicate that in the comment section below, because there is always room for enhancement for the teaching. So if you have any comment, any suggestion, please do share it with me. It will be beneficial for me. And I'm uploading all of my videos, number one for my own first fellow Americans, and then for other people, other side of the world, whoever can hopefully benefit from them. And I hope that my videos are beneficially, and as you have noticed, every of my lectures, I do not give any kind of recipe following method of teaching, but I demand justification, and I go through the justification of that. And that is what mathematics should be taught, and that is the way a student should kind of demand learning it that way. Then anxiety of mathematics will be melted away, and the mathematics becomes very, very sweet and beautiful subject. Okay, then, again for the second time, I thank you for watching, and as always, I wish you prosperity and good health, and please stay and remain safe. So long. Ay, ay, ay.